Nobody's seen this lecture because I'm inventing it as I go along. I actually have about a 4 or 5 hour sort of comprehensive discussion of statistical MT, some of which Stefan has already done a nice job of. I'm going to try and boil this down to an hour and 15 minutes or whatever it is that we have here. So my plan is the following, and plans are made to be diverged from, but here's the plan. I'm going to start out by giving you more of a 30,000 foot view of statistical MT. Then I'm going to drill in a little bit further into a couple of different areas, and we'll see which we cover, and we'll also see which you're interested in. One of them is the modeling that goes on in a statistical MT system. The second is how decoding takes place in a statistical MT system. And the third is the progression. You've already seen a bit of the progression from word-level models to phrase-based models. And one of the innovations that's taken place since about 2005 has been a progression from that to what are sometimes referred to as hierarchical phrase-based models. And those are essentially, formally speaking, actually, underlyingly, there's a synchronous context-free grammar. And intuitively, it's phrases with holes in them, or phrases that allow variables in them. And that's kind of an interesting development as well. And the decoding is a completely different animal for those, as Stefan mentioned briefly, and I'll talk about a little bit more. So please feel free to interrupt with questions, and I may ask you for your guidance at various points. Okay, so I'm going to use the board, and what I'm going to work on here is actually the big diagram of what it's like to do work in statistical MT. You can all see that from here, right? And I'm going to try to reproduce this diagram, giving you pieces, and Stefan's already given you some pieces, like here's where you do alignment and symmetrization of alignments. So you can see how it all fits together. If this were one big, huge board and I had a step stool, that would be really easy. I think I'm going to have to modify this on the fly as I do this, but let's give it a shot. So where do things begin? Things begin here by breaking chalk. Things begin here with a bitext or parallel corpus. And already we could start having a conversation here and go into another hour's worth of discussion. Where do you get the bitext, right? What does it mean for these things to be aligned with each other? Sentences to be aligned with each other. How did you get those in the first place? There's a lot of richness here. What kind of pre-processing do you do on the corpus? For example, do you map the Roman character set to lowercase? If it's Chinese, how do you break the thing without spaces into token sequences? If it's Arabic, do you split off al from the word that it follows? A determiner tends to be attached, and other sort of clitics. Morphological analysis. So there's an enormous amount of richness, even just in this little abstract box that I've written here. So in some sense, what I'm doing is giving you little bookmarks, pointers to other things that can be looked into or asked about in discussion here. Nonetheless, let's assume we have a bitext. Let's assume that some pre-processing on this thing has taken place, so it is tokenized. And the units here are, for the sake of argument, let's say sentences. And these things are putatively parallel to each other. In other words, these things are translations of each other. That varies a lot. If you've looked at translations on the web, even human translations on the web, that can be true sometimes and sometimes not. Here, we have word alignment. Stefan has already done a nice job talking about that, so I'm not going to drill down very far inside this box. The typical thing that one does is you run, I mean, other people do other things, but you run Giza++ in the two different directions because of this fertility asymmetry, right? And then you symmetrize somehow by combining things. So take the union, you're going to get a lot of alignment links. Take the intersection, you're going to get a much smaller number, but they're going to be very confident alignment links. And what's more typical is to somehow, for example, take the intersection and then go build from those confident links out to more links that you can add in order to build more alignment points in that. Why do we do that? Because we don't know any better. The model for what it means for two sentences to correspond to each other has not evolved significantly since Brown et al. started doing this stuff in the late 1980s. So we are actually making a very stupid decision to start with, which is we're beginning with the idea that word-to-word relationships at the level of tokens is somehow the basis on which we're going to build our notion of translation. But like many other things, say n-grams in language models for speech, it's a reasonable first approximation. And so we're focusing our energy on doing other things. At any case, you get the word alignment out. So out to here, you get one best alignments. So here is, say, E, and here is F, and you have alignment links. This maps to this, and you can get some reorderings, or you can get multiple alignments and so forth, right? Now you've got a big aligned corpus. By the way, I've already left out a little bit more richness here, so let me just put a couple of pointers in here. Sometimes this thing is too big. At Maryland, we work on machines that have 8 gig cluster, about 18, 20 machines. The Hopkins cluster is actually significantly more enjoyable to work on because you got more machines at your disposal. Well, it's 2 processors per, but 8 gig of memory limits you a bit. So one of the things that is sometimes done is called subsampling. So you take the set on which you're going to be evaluated, and you say, you know what? Any pair of sentences here that has no overlap whatsoever, even at the level of unigrams, with something in my test set, I don't care about. Be careful. Looking at the test data can become cheating, right? But this is an allowable sort of thing because it doesn't actually affect the models that you're going to do. It's just streamlining the process. Your results are not likely to change. And so sometimes you do subsampling looking at the test set in order to do alignment on a smaller set. And so you can go from tens of millions of sentence pairs down to hundreds of thousands or millions and get better data. Okay, so now what do we do? Let's see. I'll do it this way. Okay, this is kind of cool. Overshot there. So at this stage, we have another box. I'm going to call this phrase extraction. Again, Stefan has talked about this. There is this heuristic that's used that basically says, look for units on the source and target side such that you have reason to believe these units map to each other as phrases, for example, word-level alignments, and avoid the situations, or just forget about the situations, where something inside one phrase at the word level maps to something that's outside the other phrase. Right? That's essentially what that heuristic with the sort of the grid and the dots is telling you. But it's just a heuristic. Right? And it's important to remember that. So phrase extraction is something that takes place on an aligned corpus there and produces what is usually called a phrase table. So what do we mean by a phrase table? Let me go over here and do this on the side. If you want to actually get a very crisp, quick introduction, just reading through, look at the introduction to this. Philip Kuhn is responsible for this system called Pharaoh. Who here has actually encountered Pharaoh before? 1 or 2, okay. Pharaoh is publicly available, and by the way, the Moses system is its descendant. There's a whole history that comes out of this Hopkins summer workshops. There was originally a system called, a piece of software called Cairo, which actually stood for something. And that led to an Egyptian theme. So Cairo led to Egypt, the Egypt toolkit of which Giza was a part, and then of course somebody improved Giza, so it became Giza++. And what else am I leaving out? So then you had the Pharaoh, which was essentially sort of your decoding framework, and Moses, which beat Pharaoh. And so anyway, if you look at the user manual for Pharo, he gives a really nice, crisp discussion that will give you a strong sense of what phrase tables look like, what the decoding algorithm looks like, and so forth. It's there on the web. If you search for Pharo Kuhn, chances are you'll find it. Pharo user manual. At any rate, in the phrase table in a system like this, basically what you have is a phrase f, and I'm going to use the bar over the top. I'll try to be consistent. I'm going to use the bar over the top when these things are phrases, in other words, contiguous subsequences of tokens, as opposed to without the bar, which I'll try to use for words. Right? So f, e, right? These are the phrases on the, I'm going to assume that English is the target language, and F is the source language. And I think Stefan has already mentioned to you that if you take a noisy channel model, the source in the noisy channel model is generating what will ultimately become the target language, right? F, sometimes you will hear people slip and say, so we take the French sentence and we do, and you say, wait a second, this paper is about, or this talk is about translating Chinese. People are very confused about this. So F sort of is interchangeably French or foreign, all of which is still a very English-centric view, right? And that's because the guys at IBM started with the Canadian Hansards as the parallel corpus that they were working with. And by the way, that decision has had major implications for the development of statistical MT. In the same way that the fact that Chomsky's original stuff was largely with English has had major implications for the development of syntactic theory. If Chomsky had been born into a place where and been working in a place where, for example, you had an agglutinative language, chances are that syntactic theory would have looked very different as it developed, right? Similarly, with the IBM models, because English and French are similar to each other in certain ways, right? This has been a development. As a very simple example, it was okay to make an efficiency decision that you could have alignment links in the generative process, right? So this concept here that you can go in this, you can split in this direction generatively, right? But not in this direction. That asymmetry? That works okay for English to French. Not and ne pas, right? Ne, verb, pas is the way that you say not verb, right? Je ne parle pas français, right? I know. If that phenomenon works because that's the way that it's expressed in English and in French, right? If you had a lot of this stuff going on and you were trying to translate into English, they probably wouldn't have developed their model. They probably wouldn't have left that asymmetry in or made it impossible to go in the other direction. So there are implications of the data set that you're working on. And that's actually a general thing. If you guys have worked in speech or anything else, the particular data set that you work on has a great deal of influence, which is why any of you who have looked at the parsing literature should, if you're not already, be intensely frustrated with sections whatever through whatever of the Wall Street Journal, which is like the most overused and abused data set. I don't want to say in history because there's probably others. At any rate, in a phrase table, you have the phrases that you've pulled out, and there are also what are generally called features associated with this phrase pair. So typical features that you might find. Probability of F given E. This is the phrase-to-phrase generative direction probability, right? Probability of E given F. This goes in the other direction, right? Something that's called the lexical weight between E and F, and I've left myself out of room here, F and E, right? This is something that actually looks inside the phrases. By the way, these are estimated typically through maximum likelihood estimation. Nothing fancy. Go ahead and count, right? In fact, it's even more depressing than that. People have done studies and showed that if you take the probabilities, these things, and you actually discretize them by storing them in only a certain number of bits, right? So you're bucketing the probabilities for efficiency's sake. What is it, Stefan? I think it turns out the performance is just as good if you go down to like 4 bits, if I recall correctly, per number. You're not hurting your translation performance a lot. The probabilities do not need to be incredibly fine-grained.
This actually depends on your data size, both for language model and for phrase table.
Yes.
If you have very large data, then you can use fewer bits.
That's right. That's right. At any rate, you have a whole lot of features that will go into, and at the time that you're extracting the phrase tables in this big picture, you're also typically computing these features and storing them in the phrase table. Right? By the way, that approach means that if you want features to be sensitive to something outside the phrases themselves, for example, what's the probability of translating E bar as F bar in a particular context? Maybe pay attention to the part of speech tag of the word to the left, right, of the source phrase. You're going to blow up your phrase table, right? All of a sudden it gets much, much bigger. And that's a problem. And so as a result, virtually everybody is just using features of the phrase pair, right? Le chien, the dog, right? And this is really problematic because, for example, say el gato in Spanish, right? For those of you who speak Spanish, means the cat, right? Except, as a Spanish-speaking student of mine told me, when it means the jack in the sense of the thing that you use to change a tire on your car. Ah, yeah, that surprised me also, right? So this phrase, the phrase level features for this are not sensitive to the context, right? That's problematic. And right now, that kind of disambiguation is largely done by the language model, which pays attention only to the target side. That's a difficulty. There are 2 things that have been done relatively recently that get past this approach in an interesting way. One is some work by Maureen Karpawat and Dakai Wu, and they take word sense disambiguation techniques and apply them essentially on the fly. So they turn this probability into a context-sensitive probability. They're generating phrase table information in some sense on the fly in order to make this probability sensitive to the context. So for example, one would assume that if you see the Spanish words for tire and car, right, somewhere in the vicinity, the probability of gato being translated as jack should go up, right? And they are the first people to have gotten any real result using word sense disambiguation techniques at all in machine translation. And I say this being one of the other people who tried to get WSD to do something useful in machine translation. A student and I tried to do this, but we were looking at the level of words. Their key innovation was to generalize from word sense disambiguation to phrase sense disambiguation. Right? So taking a phrase and mapping it to an enumeration of possible phrases in the other language looks a lot like a word sense disambiguation problem bumped up to the level of these phrases. That's pretty cool. The second thing that's been done is instead of computing a phrase table in advance at this stage, this big picture gets modified. And instead what you do is you store the entire training corpus along with the alignments. And you actually extract your phrases on the fly. And so Chris, is he still in here? No, he's disappeared. Okay, that was smart of him. Was one of the people, and Stefan is one of the others, who introduced the suffix array data structure as a way of doing efficient storage and retrieval, storage of the corpus and retrieval of individual phrases. So that you could basically say, hey, I've got this phrase, you know, el gato negro, and I want to, instead of in advance creating a maximum likelihood estimate for that translating to the black cat versus the black jack versus whatever else, right? I'm going to actually look for every place in the training corpus where I find this phrase, on the fly. Go find those places where it occurs. And now look at how they translate it. And by doing it on the fly, you can now pay attention to context, right? The trick is doing it efficiently on the fly. right? Oh, I'm going to, grep through my corpus? That's not going to work, right? And so the suffix array data structure solves this problem, and a student of mine, Adam Lopez, who's now at Edinburgh, it's all very, very incestuous. He's now postdoc at Edinburgh working with Philip Kuhn, among others, actually in his dissertation generalized that whole suffix array-based approach to hierarchical phrase-based models, right? In other words, you can actually search for substrings with holes in them efficiently. And that was a real scalability problem for the standard suffix array approach. Okay, so having digressed off to here, and you're getting a sense of my style, right? It's just going to be a little bit of wandering, and then this thing's going to keep me from going completely off, maybe. So we extract a phrase table. I've already shown you what the phrase table looks like, so I'm just going to draw that here as phrase table, right? That thing over there, right? And this, let's see, where do I want to go? I'm going to reverse this over to here. This goes into parameter tuning. Okay, now wait a second. We're missing a couple of important things here, right? One of the important things that you should see that we're missing is the language model. This thing, the phrase table, is the incarnation of the translation model. It's about the mapping from French to English, source to target. The language model does a ton of work, just like it does in speech systems. And so where does that fit in? Well, somewhere over here, in addition to that, bytext, you also have a monolingual corpus, right, of the target language. And from that, you're going to build, let's see if I can make this reasonably, you're going to build a language model. What kind of language model? Any damn kind you want, because it's just the target language. And so typically, you just inherit that stuff from speech. In fact, I'm not aware of very much work in language models for MT that don't simply apply equally well to speech. That's changing, by the way. What's starting to happen now is people are starting to pay attention not just to generating sequences of tokens, but to generating structures. That's where this hierarchical stuff comes in. And so now you can actually start talking about language models that pay attention to things like dependencies between words in the sense of syntactic dependencies, right? And so that stuff goes all the way back to what Chelba and Jelinek, and has descendants in like some of the stuff that Sanjeev Kudanpour has done. You should sense a theme here of where people are interested in doing this stuff. There are other and actually one of the most interesting recent developments, like this year, is work out of BBN, Bolt, Baranek, and Newman, where they've developed a model called HierDEC, H-I-E-R for hierarchical, or DEP, is it DEC or DEP? I can't remember. Anyway, but what it is essentially is it is a hierarchical model, right, where you actually are generating on the target side, you're generating dependency structures. Right, so strings on one side, trees on the other. But the strings on one side are these things with holes in them. And the way that it gets the bulk of its bang for the buck is that it has a structurally based language model on the target side. People have tried that before, but they actually haven't used a translation model that naturally feeds into that kind of thing. One thing you don't generally want to do is generate stuff with your hypotheses with a string-based kind of approach, and then just take a tree bank trained parser and try to parse those things. That tends not to work because those things aren't English, right? They're MT hypotheses, and sadly, most of the time, that's not English. It's something you're trying to get to be more and more like English. And so this recent work out of BBN is actually a very nice piece of evolution. So there is, in fact, an evolutionary path, if you think about it this way, from the word-based IBM models, model 1 through 5, et cetera, to the phrase-based models that Franz Auch introduced, to the hierarchical phrase-based models that were introduced by David Chang, to these hierarchical models that actually take some parsing information into account, but in an intelligent way. So there's a real line of descent of evolution running through there. So I'm going to assume we're just talking about a language model in the sort of traditional n-gram-based language model sense. You want it as big as you can get it. You want to do all the good smoothing stuff that you do and so forth. Typically, SRI language modeling toolkit. That's typically what you're going to find with 5 grams, and if you can do bigger than 5 grams, great. If you've got the data and the machines for it, Knesser-Ney, smoothing. I mean, just that standard kind of off-the-shelf stuff is very, very common. Again, lots of nuance. Should your language model be tailored for your test set? Should you perhaps interpolate multiple language models, right? If your test document, say, could be from multiple possible different genres. If it's labeled with a genre, to what extent do you want to just use the language model for that genre, which might be smaller, or interpolate that, and if so, with what weights, with a general language model that crosses all genres? So again, lots of nuance there, even just in the language models. Okay, so the language model is obviously also factoring in to parameters. Does this work if I'm doing it this way? It kind of looks like it's supposed to. Good, this is great. Okay, so when you do your parameter tuning, right, what you're going to use here is dev data, right? You have source language data together with references, with reference translations. Typically anywhere from 1 to 10. Some sets that are out there, I think, maybe go up to like 16. But if you do sort of your NIST, National Institute for Standards and Technology, sort of MT evaluation stuff, you'll find a lot of stuff where you have reference 1 through reference 4. 4 references is not unusual, right? Why do you need multiple references? Why is this not like parsing, where your gold standard has 1 parse tree? Well, have you ever actually tried to get 2 translators to actually agree what the correct translation is? Getting people to agree on the correct, say, part of speech tags for a sentence, not too bad, right? There are places where there are nuances difficult. Try to get them to agree on parse tree. Inter-annotator agreement, it's not too terrible, right? There are some subtle cases. You ever try to deal with word sense disambiguation? Okay, machine translation is like word sense disambiguation on steroids. We're no longer talking about the individual words. As soon as you get into stuff that involves meaning, that really has to involve meaning, you ask a bilingual, hey, is this the right translation? If they didn't translate it themselves, they're going to say, yeah, I wouldn't have translated it quite that way, but yes, I guess so. And so how do you actually deal with this? You have multiple reference translations that come from multiple translators, and then you define correctness in a way that takes the multiple translations into account. Has anybody mentioned blue to you guys? Yes. Yes, great, okay. So that, in a sense, is what blue is designed to do. It's designed to give you an automatic metric so that you don't need humans in the loop, so that you can use it every day or every hour, every run, right, in order to see how well your system is doing. And by the way, then it became bastardized into a way of evaluating how one system performs against another. But that's actually not the original sort of idea behind it. The original idea behind it was formative, not summative evaluation, right? To see how well you're doing as you go along. So you have dev data, and you do parameter tuning, and again, just like there's, well, what do people often, what's this vanilla people usually do? Giza++ and the symmetrization for that, and, SRI language modeling toolkit. For parameter tuning, what people do is something called minimum error rate training. There are other things that people do, but this is, again, sort of your standard high-level view. Minimum error rate training was introduced as a way of optimizing your parameters for whatever objective function you're using to decide if translations are good. Up to that point, people were using a more typical kind of maximum likelihood criterion or something, right? Optimize the parameters, right, in such a way that my model is most likely to have generated this development set, right? what do you think? If you actually come up with an algorithm that optimizes for the score you're being evaluated on, it's going to do better on the score you're being evaluated on. So the paper that introduced it had a nice grid. Here are 6 different scores I could be evaluated on. Here are the 6 different ways, scores that I use for optimization. Big surprise, the stuff on the diagonal has the highest score, is doing the best. Right? So it's valuable to optimize. There's a problem with this. The problem is, boy, you'd better trust that your objective function, in this case, say blue, which is used very frequently, actually maps to better translations. And there lies religious warfare. There's a whole community of people who, somebody, maybe York Wilkes, was quoted as saying something to the effect of there are more approaches to machine translation evaluation than there are approaches to machine translation. And this is not a joke. And that was before Blue came out, right? There was a European project, right, where the entire project was to create a taxonomy of ways to evaluate machine translation in the literature, right? And I was paying attention to lots of other things, software engineering things, efficiency. There are other things you can look at beside translation quality. By and large, the human evaluations tend to focus on accuracy and fluency, right? To what extent is the translation actually conveying the meaning, and to what extent did I get something readable? These are not distinct, right? They overlap. That's the human evaluations, and what Blue is doing is doing, as you saw, an n-gram overlap metric, right? A precision-oriented n-gram overlap metric that is basically getting at fluency through the sort of the longer n-grams are better aspect of it, but also getting at fidelity or accuracy, because what you're doing is comparing against reference translations. So there's an element of both of those things inside the Blue metric. These days, you can pick from a list. Out of CMU, there's a metric called Meteor. Meteor is, and I'm not going to go, this is a whole nother, God knows, 10 hours on MT evaluation. But Meteor is commonly used. There's something called TER, translation edit rate, which is essentially a generalization of your typical string edit distance, except that if you move a sequence from one place to another, that only counts as one operation. Now, why would you want to do that if you're evaluating machine translation? Well, because look, if I take a whole noun phrase and I move it from here to here, should I really get penalized, more because the noun phrase is longer? So TER is actually widely used, and within the Gale program, which is the Defense Department funded push on machine translation, which funds a whole lot of people in the community, they use a variant called HTER, where you're looking at the translation edit rate, but you've actually got a human in the loop in a way that I won't go into details, but ask me about it afterwards. In effect, it simulates having the size of the set of reference translations being infinite. That's my interpretation of what HTER does, because you've put a human in the loop. So at any rate, you want to tune your parameters. Well, okay, if you're tuning the parameters, you're tuning the parameters of a model. Okay, now the digression. Let's go here and talk about the model, right? What is standardly done? In the noisy channel model, it was a very, very simple picture, right? You had your source model, so that's good. I have, P of, let's see, how do I do this? I think I'm going to use capital E here to represent the English sentence, right? So I generate my source with that probability. I generate my target through the channel with this, right? And through the miracle of Bayes' rule, right, you can essentially argue that that if you want to optimize, right, you want the argmax of the source, the target given the source, P of E given F, what you want to actually be optimizing is the product of these things, right? The miracle of Bayes' rule plus there's a constant in the denominator and you don't care about it, right? So intuitively, this may not be how it developed, but intuitively, think about it this way. This is giving equal weight to these two models, right? The language model and the translation model. Why should they get equal weight? right? Maybe what you really want is, lambda 1 up here and lambda 2. It's a product, so I'm going to use the exponents here, right? Okay. So maybe I actually want to be able to weight these things differently. Right? Okay. Well, let's go into log space, because now it's going to look a little bit cleaner, right? So now I've got, lambda 1 times 1 log prob plus lambda 2 times this other log prob. Right? So now I've got what's called a log linear model. Okay. And then you look at this and you say, well, that's pretty cool. But why the hell should I stop with these two features now? It's not a probability model anymore. Right? My generative model justification for doing it is gone. So there's absolutely no reason in the world not to generalize this, right, to the sum of your lambda sub I times some features of E and F and who knows, maybe some other things there. And so this is commonly what these models look like now. And what are these features? Well, hey, here's your, I'm sorry, I left out, yeah, well, look, the translation model is not going to contain P of E, right? But it's there from the language model, right? The translation model related features, hey, yes, P of F given E, there it is. But hey, why the hell not throw in P of E given F too, right? Some people have found that it helps. Other people have found that it's kind of redundant. A lot of art and science going on here. There's this lexical weight feature that I mentioned, but didn't really tell you what it is. This is done by maximum likelihood estimation, looking at co-occurrence of the entire phrase. Well, let's suppose we've never seen these two. I've only seen these two phrases together a couple of times, right? But let's suppose that the words in the phrases map to each other really strongly at the word level. Well, then I might want to say, hey, I think this phrase pair should get a lot of credit in my model. Right? So the lexical weight is basically, you can think of it as something like IBM Model 1, which you just saw. So it's kind of summing up, looking at possible alignments of the words in the phrases. You can think of it as a variant of that. And because you're assuming that things are asymmetrical, you actually have the lexical weight going in both directions. You can have other features too. You can, oh God, it goes on and on and on. There's lots of different features that you could have here. The important part is that you have a log linear model that combines them. That's the typical thing to do, right? Another nice property of log linear models, have you guys looked at maximum entropy modeling? Many of you guys have. Well, a really cool thing about going from a generative framework to a log linear framework is you no longer have to care about the features overlapping with each other, right? That's huge, because I don't have to design some EM variant, some new EM variant as soon as I have a new feature in my model that somehow I have to tell my generative story and somehow figure out how to calculate this. I just throw in another feature, right? With one catch. If you throw in more features, then your parameter tuning problem gets harder, right? And you have two different difficulties. One is the potential of overfitting, and the other is the potential that minimum error rate training is going to croak. Because it turns out in practice, 5 parameters, no problem. 8 parameters, no problem. 11 parameters, probably no problem. 20 parameters, It's just going to, forget it. There's a scalability issue here. MERT just dies when you give it lots of parameters. I'm actually working right now with David Chang. There's another parameter approach that we're trying. If we're lucky, we'll have an EMNLP conference submission next. I think Tuesday is the deadline. Thursday? Oh, you just made me so happy. So yeah, next Thursday then. Good, more time to write the paper. More time to get the results and then write the paper. At any rate, minimum error rate training leaves you with the ability typically to only optimize a smaller number of parameters. And by the way, when we go back to this big picture, we should look at the bottlenecks that people have. In our lab, Giza used to be the big bottleneck, aligning thing took a long time. I mean, decoding is relatively fast, right? Minimum error rate training is actually the real bottleneck now, right? Because what minimum error rate training is essentially doing is it is decoding the development set. It's doing a comparison to the reference translations. And then it's following some delta in the parameters in the search space, right? So it's an iterative sort of thing. It's a hill climbing kind of notion, right? And when that happens, you're basically decoding your dev set over and over and over again. How many iterations is it going to take? We'll give you a sense of the scalability, the scaling for us in my lab, where we've got an 18-node cluster, each of which has 4 processors on it. But for decoding, typically we'd only use 2 at a time. Otherwise, we're going to run into memory trouble. We use smaller language models than many other labs for that reason too. Anybody want to donate some machines to the University of Maryland? Typically, the kinds of test sets that you see, say, in the NIST evaluations, where you're talking about 1,000 sentences or something, I don't know, maybe half an hour for a decoding run to decode in parallel on our cluster. Minimum error rate training, you could go through anywhere from 4 to 14 iterations, say, before it converges, right? That's not fast, right? Figure 7 hours to optimize your parameters. You can do basically 1 experiment a day. Boy, it'd be nice to do stuff a lot faster than that, right? And by the way, you have to optimize the parameters because they make a huge difference. We've done experiments where you didn't optimize the parameters, and you do. And if you look at the blue score, where realistically speaking, if you get, say, a 0.3 difference in blue, you kind of say, it's in the right direction. If it's 0.5 to 0.7, you kind of say, looking good. 1, you say, I may have a publication, right? 2, you typically, disagree with me if you want, Stefan, if you disagree with how I'm calibrating. I see you smiling. 2 points, you say, I've got a strong publication. All of this depends on the size of your sets, obviously, right? Statistical significance and the meaningfulness of it. But and anything above 2 is, I recommend to my students that they use the word substantial in the abstract of the paper when they're talking about the improvements in performance. It's sort of a visible improvement in how well you're performing. So this parameter tuning is a real bottleneck, but it makes a big difference. And so it'd be nice to improve it, which is one of the things we're working on now. Okay, so. Is this all going in the right direction for you guys? I'm not going into details of decoding yet, for example. Should I finish this high-level picture? The digressions are now telling you useful things as I go along? Okay, that's sort of the strategy. So I left out here your evaluation criterion, which is typically blue. And typically there's a script that everybody runs. It's really important actually to have the same script as everybody else is running because they're very, detailed. Sometimes it's like, oh wow, I got this big improvement. Oh wait, you're using this version of the script and it does things slightly differently. And to avoid disappointment, you want to do that. Okay, so we have, coming out of this parameter tuning process, lambda 1 through lambda sub k, where k is your number of parameters. Be careful. When I say parameters in this context, I mean this small number of parameters or lambdas in your log linear model, right? There are other kinds of parameters that we talk about also. Every probability of an n-gram is a parameter in the language model, and all of these are parameters in my translation model, right? So when we say parameter tuning, in this case, what we're talking about are the parameters in the big model that rolls everything up together. Okay. Having done that, oh, and I left out something kind of interesting here. As I mentioned to you, the decoder lives inside this parameter tuning process, right? If you change the decoder, everything changes, right? Okay. So we have our optimized parameters, and now these parameters are going to go up to, just bring this thing down here, okay, there, and this now is going to decoder, which I'll write down as decoder sub lambda bar to indicate that this is parameterized by that vector of lambdas a second ago, right? And our decoder has the same evaluation criterion, say, actually, I don't think I want to draw it there. I want to draw it as a separate box, right? So you have your test items, your test set, which is just source, obviously, and this is going into your decoder. And out of the decoder, What comes out of a decoder? That's an interesting question. The obvious answer is a translation. Is that true in speech? Is what comes out of a decoder a transcription? Well, yes and no. Sometimes it's not one, it's and best. Sometimes it's not and best, it's a lattice, right? And you're going to do other stuff with it, right? So I'm just going to write hypotheses and let the plural be ambiguous for me. Right? These are the hypothesized translations. And you can do a bunch of different things with these hypotheses. You can simply evaluate using something like BLEU or Meteor or something else. Another thing that you can do, if you've got n best, is you can rescore. You can do re-ranking, like you do in speech systems. Now, there was something a little bit misleading earlier when somebody mentioned the smorgasbord paper, the Hopkins summer workshop, where they tried a bunch of syntactically based techniques in MT, and they turned out not to work very well, right? In fact, they turned out depressingly not to work very well. You had a bunch of really smart people throwing a whole bunch of things at it, and the only feature that turned out to actually create any improvement was IBM Model 1 at the level of the phrase, the pairs of phrases, right? Or maybe it was the hypothesis, at the level of hypothesis, I can't remember. That's kind of depressing, right? But here's an important fact. They applied these features in a re-ranking, a rescoring framework, not inside the decoder. Right? Now, there's justification for this. They did an Oracle experiment where they took your, say, 1,000 best, right? And they said, hey, look, if an Oracle could tell us which the best one is, we have things with much better translation accuracy and fidelity and fluency, better performance in this n-best list. So it's perfectly justifiable, right, to say, let's just take a reordering kind of approach, right? Just find a way to boost that thing up to the top. And by the way, they went with 1,000 best. They were trying to decide the optimal size. They went up to like 16,000, and they didn't get as much gain as you would hope. They decided 1,000 was big enough, right? There was a lot of room for improvement. But one could argue, in fact, that letting these things duke it out inside the decoder is actually, and optimizing the parameters using minimum error rate training is actually potentially a better way of doing it. And so one of the nice things about these suffix array approaches, for example, is they allow you to use a rich feature space by computing features on the fly, rather than having to blow up your phrase table doing that sort of thing. So then you go to the test set, and you can do things like rescoring. You can do things like evaluation, all of that with the test set and its own set of reference translations. Okay. Oh, and then, by the way, let me mention this is the end of the story as far as most MT work is concerned, right? We get sentences in. We get a training set. We have, where'd it go, a test set we want to decode, right? We want to see how well we did. We publish a paper and we're done. I don't want to leave out an important concept. Why are we doing translation in the first place? To publish papers and get tenure. Okay, yes. All right. Because it's fun, yes, some of the time. To get funding, yes, some of the time. But in general, we are translating for a reason. MT is there to help somebody do something, right? So I just want to mention at least that there's a very important distinction, and this isn't just about MT, this is about everything, between an enabling technology and an application, right? So parsing is an enabling technology. Nobody wants parsing. Sorry. People want parsing because it helps them do something else. Because they hope it helps them do something else. Believe me, replace parsing with word sense disambiguation. You're talking to the guy who wrote the book. Actually, I wrote the chapter. There's a book on word sense disambiguation that came out a year or two ago, and I stupidly agreed to write the chapter on word sense disambiguation in natural language processing applications. For those of you who know anything about the history of word sense disambiguation, word sense disambiguation has had almost no useful role whatsoever in natural language processing applications. It turned out to be a really difficult chapter to write. My first draft, the editor sent it back and said, couldn't you be a little more positive? Go read the chapter if you want to see the way I tap danced around and found, anyway, but don't tell them I said that. An enabling tech. Say again? You have to go back and edit it. And it's a great book. You should buy it just to read this chapter. They don't care as long as you pay the price of the book. So the moral of this story is that there are what are called intrinsic evaluations. That's looking at the particular piece of technology you're evaluating on the terms of whatever task, subtask, it's trying to solve. Say, parsing or word sense disambiguation. Then there is what is called extrinsic evaluation, where you look at the effect that that component has on the system as a whole using some external criterion. So for example, let's suppose that Google decided to be doing word sense disambiguation inside, right? They would be evaluating the effect of word sense disambiguation, not by measuring WSD quality. The measure that would really matter, well, a measure that would matter more to them, right, would be the effect that the sense disambiguation component had if you did search with it and search without it, or search using different variations of it. Of course, then you say, well, what actually matters to them is actually how many ads people are willing to put on the page if they've changed their search in a way that does this. So you go beyond extrinsic. Oh, by the way, I very stupidly agreed to write an entire chapter on just evaluation in NLP. And so you can see I've been thinking about this stuff recently. So in the case of machine translation, right, MT is there to help people do something. And so you can evaluate it intrinsically, which is essentially what something like the BLUE score is doing. Or you can evaluate it extrinsically by, for example, sitting a human being in front of a computer trying to solve a problem that involves documents in a language they don't understand, and measuring the extent to which it helps them solve that problem. I have colleagues at Maryland who are very into this stuff. Doug Ord, O-A-R-D, does some very nice stuff along these lines, for example, where you're looking at the human-computer interaction, you're looking at the information needs, and you're looking at the way that the translation system is actually helping them solve the information needs. So there's a lot more to the world than decoding, and even improving the performance of translation, which already seems pretty big. And I just wanted to mention that. Okay, so at this stage, I've given you a 30,000-foot view. There are a couple of things I could do now, one of which is stop or take questions. Another of which is to say a bit more about, here are some possibilities, decoding, or these hierarchical models, or I could say a little bit actually about some recent stuff that we've been doing at Maryland where you're actually translating not sentences coming in, but lattices coming in, and why that's a cool thing. So any preferences? Stop is okay too. Votes for stop? Okay. Votes for, who wants to hear about, say, decoding? Who wants to hear about hierarchical models? A couple of people. Cool. Who wants to hear about lattices? These things are actually related to each other. So let me see if I can manage both of those things very quickly. Hierarchical modeling. All right. So there's a problem with doing MT in the phrase-based model. There are a variety of problems, but there's one that seems pretty clear. And that is that you are failing to capture generalizations, right? So if I have a phrase pair that says, el gato negro, the black cat, and I have a bunch of features associated with this, right? And I happen to know that the word for a dog in Spanish is perro, and I can't roll my R's, I'm sorry, but I think you probably would in this case, P-E-R-R-O, right? Let's suppose in the training data your system has never seen, right, el perro negro. Well, damn it, if you know these two things, you should be able to translate el perro negro, right? But in a phrase-based model, you might know that el goes to the and negro goes to black, and you have two choices. You've either memorized the entire phrase, right? Or you've got individual pieces, right? And you have to put them together. And here's the problem. The problem is sometimes the individual pieces, look, right, so this is, the cat, and this is black. Well, the problem here is that black goes inside here, right? So if you break it in all the way down to words, you have reordering issues. If you break it down, memorize the entire phrase, you can't generalize. Here's what you really want. What you really want is to be able to say, hey, el X negro, right, in Spanish means the black X. That's the actual mapping that you'd like to have intuitively, right? Yes, that's right. For example, you might like to be able to have something like el gato X, potentially, right? The X cat. Now, of course, you run into trouble with this by using one single symbol here, X. Nobody says, in this context, this thing had better be an adjective, right? So if you were saying, the cat went into the black house, right? Then this thing, right, might be some weird non-linguistically sensible thing, but still fit in just as well. That's an issue, but you know what? We're not going to worry about that at the moment. So what ended up happening was, if you look at this, if you think about it, God bless you, let's suppose that I have me gusta X, I like X. This is another phrase mapping, right? And let's suppose we've also got gato mapping to cat. If I get a sentence like, as my source, me gusta el gato negro, and I want to translate it, right? I can think of translation. Now, you can interpret this thing, this phrase table, actually as a context-free grammar, as a synchronous context-free grammar. What I'm saying here is the non-terminal symbol X maps to, a synchronous context-free grammar is basically where you have a single grammar, in effect, generating two strings at once. Or if you want to think of it, you can think of it as two synchronized or aligned grammars. So such that if I expand this non-terminal this way, I'm expanding the corresponding non-terminal that way, and the this way and the that way are linked to each other. For example, via phrase table entries like this. Okay? So this, by the way, and people get into trouble all the time by not doing what I'm about to do. This important concept can be traced back to work by Decai Wu in the mid-1990s. There was an approach that he took called inversion transduction grammar. It's actually worth mentioning that and looking back at that stuff because it anticipated many of the things that came out since then. So the basic idea here is if I interpret this thing as a grammar, right, then translation can be thought of as find me the parse tree for this that gives me the best translation into English. Take a second and get your head around that, right? Parsing generally says, I want to parse this, so parsing is decoding. Is everybody comfortable with the idea that parsing is decoding? Parsing is a search through the space of possible analyses guided by a model. What's decoding? Search guided by a model, right? Except in this case, what we're doing is generalizing such that the search is guided not just by the monolingual syntactic model of some kind. In fact, we're going to get rid of the monolingual syntactic model in the tree bank sense altogether. This is tree bank free parsing, Okay? You're going to learn your grammar and your model directly from the bilingual text. And having learned that grammar, you're going to do your search through the space of analyses of this thing, guided not by some monolingual parsing model, or syntactic model, but guided by that entire log linear thing that we were talking about before. So it's a small but very, very significant leap which was made by David Chang at Maryland in about 2004, 2005. He's now at ISI. So here's the idea. Of all the different rules in this grammar, so now I'm going to do a bottom-up parse. People familiar with bottom-up chart parsers? Early's algorithm, that sort of thing? Okay, so just think of this as a bottom-up chart parser that operates from left to right, so it's kind of like CKY plus, right? It has dotted rules, you move the dot, and all the rest of that good stuff as you're parsing bottom-up. I might have me gusta X, right? Okay, so me gusta X, I like X. Oh, good. I have a rule that will take care of me gusta, right? X goes to, well, actually, I don't want to, sorry. I'm going to pretend that I don't care about going left to right, just for purposes of this example. It's much easier to illustrate going bottom up, right? Okay, so gatto, right? There's X goes to gatto. Oh, and by the way, while I'm doing that, you guys don't need to see these rules, they're pretty obvious, right? So while I'm doing that, I'm recording the fact that the rule that X goes to gatto, its synchronized partner on the English side was X goes to cat. Oh, look, I've just built a little piece of a translation, right? Again, leaving out the fact that this is done left to right. I'm just going bottom up. X to cat versus something else? Well, how did I choose this rule rather than some other one? I used my entire model. I used the language model, I used the translation model, I used whatever else it is. Okay, great. So, okay, now I have forgotten my rules. Oops. The black X was LX negro, right? So I can go bottom up here again, right? So X goes to LX negro, right? And its rule pair here was the black X. That's too high. Okay. So, right, I've gone bottom up here. And by the way, when I made this decision, now you can start seeing where the language model fits in, right? As I was deciding to build this piece of tree bottom up on the source side, with its consequences on the target side, I also evaluated, hey, how good a trigram is that? How good a bigram is that? Right? So the language model is actually a part of this process, as are all these other features. One more step, me gusta X, good. So I have an X goes to me gusta X, and I have I like this. Again, I have my rules that I used. And so my decoder actually produces an entire synchronized derivation. And when I say synchronized, I really mean it. So you can think of this as X1, this is X2, this is X3, right? So decoding in a hierarchical model is bottom-up parsing, where the bottom-up parsing is guided by the model. And this turns out to be really cool because there are things that are difficult to capture in a phrase-based model, generalizations. One is you might have a phrase and then X1, and then a phrase and then X2, right? Right? This is just more terminal symbols I've left out there. And on the other side, it might be X2, X1. This is a reordering, right? In phrase-based models, reordering is handled through this weird concept called distortion, right? Distortion, again, going back to the IBM guy's English-centric view. In a generative model, we have English and we are generating French. That's how French comes to exist. The French people don't like this. When I give this lecture, I've actually given a version of this in France. I reverse it. So I don't get thrown out of the room. So the key idea there is that distortion, right, is movement of a phrase. It's a phrase showing up in a different place in terms of the order. This actually is, there is no distortion model in a hierarchical phrase-based system. Distortions are handled, these are phrase-level distortions, And by the way, the probability of this phrase pair is obviously sensitive to the words here. So there is inherently a lexicalized distortion model sort of implicit in what's going on here. And by the way, people have since introduced lexicalized distortion modeling into phrase-based translation. There are some who argue that, in fact, all of the value of hierarchical phrase-based models comes out of this sort of lexicalized distortion property. There's an interesting question as to how much of the value comes from lexicalized distortion, that ability to do that sort of thing, versus the other really cool property about these things, which is that you can handle, hey, why go context-free instead of finite state in the first place, right? It's to handle longer distance dependencies. And so, for example, in Chinese, I know exactly one word in Chinese, de. And my example doesn't include it. So pretend these things in capital letters are Chinese words. In, down, the words that you would gloss that way, right? If there's something here, if there's an X here, you can gloss in English as under X, right? This can be as large as you want it to be, right? Phrase-based models suck at that because you can only get phrases up to a certain length. You have to for efficiency purposes, right? But this thing could be 10 words long. But that's the beauty of a context-free grammar, right? It's context-free. It doesn't care how big this subtree is below that. And so the other, and sort of the intuitive, and to a linguist, I'm a computer scientist by training, I'm in a linguistics department, go figure. So to a linguist, there's something sort of heartwarming about the idea that your formalism can actually capture something that looks a lot more like a linguistic generalization, right? Where you just don't care about the size of this. It's a constituent. Is it really a constituent? Well, actually, no. There's no label here. David Chang has since then worked with trying to do a little bit more with labeling these things. Ashish Venugopal has done some stuff in that direction. Some of the other syntactic stuff that's been done at ISI, I haven't seen anybody take this model and really get a lot of bang for the buck out of creating non-terminal labels here that I'm aware of. So if it's just an X, nobody says it's a linguistic constituent. But who cares, right? From an engineering perspective, at least, who cares? In the same way that trigram models do a reasonable approximation of local syntactic relationships, right? This kind of model is not making any linguistically justified decisions, but you're still getting reasonable results, right? So that's what's going on in a hierarchical model. Okay, that's the basic idea. And this capturing this dependency, the phrase-based model, once this thing, all it can do is memorize. It can memorize specific words that go between the Chinese in and the Chinese down, and memorize the whole phrase. It can't capture this generalization. Okay? And one would think that would be a good thing. And then, of course, if you go and look at the trees, when you translate using a system like this, you find a lot of right-branching trees that aren't using, all of the dependencies that you'd want them to, but you're nonetheless getting some benefit out of it. So those are two things. To finish, let me just say a minute or two about some of this recent stuff that I was mentioning with lattices. Okay, let me erase this bit. I mentioned earlier that way up there in the upper left-hand corner, there were a whole bunch of decisions that got made, typically in advance. For example, if I've got Chinese, how am I going to segment the Chinese words into phrases? How am I going to segment the Chinese sentence into words, right? So there are different segmentation algorithms. Some of them use dictionaries, some of them are statistical. Here's a really inexpensive approach. Take every Chinese character and pretend it's a word, which works better than you might expect. It turns out that for decisions like that, which one is the best just depends. It depends on the genre, it depends on the size of your training set, it depends on the details of it's very hard to know other than doing lots of experiments, right? And then that doesn't really generalize to your next sort of testing scenario necessarily, because you might have a different size training set or whatever. It always depends. So you just kind of make these decisions, or you do a ton of experimentation for the particular case. So the idea here, which is a descendant of some things that other people have done in speech, Stefan being, again, somebody who's done much of the relevant work. A student of mine, Chris Dyer, has sort of led the charge on generalizing some of that into the translation setting where you're translating text. And here's the idea in a nutshell. I have Chinese word, say C1, C2, C3, C4, C5. Here's my sentence, right? Say, well, C6. I didn't want to be too short. What's the right segmentation of that? And Chris's idea is, don't decide. I've got one segmenter that has each Chinese word as a character. Great. C1, C2, C3, C4, C5, C6. I have another one that says C1, C2 should be a single word. Okay, good. C1, C2. I have another one that says C1, C2, C3 should be a single word. Hey, no problem. C1, C2, C3. Right? Have an arc for each of these things. Turn it into, consider it a lattice. Right? So I can get from here to here either by treating them as a single word or by having going through each one individually. Actually, these arcs should be there. That's better, right? You guys could draw the lattice on this. Good, I'm not going to. And then decode the lattice. What does it mean to decode a lattice? It turns out that you're, for example, in the hierarchical setting, that building a bottom-up parse with a sentence as its input is fairly straightforwardly generalized. When this is the input, think about the early parser. There's sort of a scan operation where you move the dot across a terminal symbol. Well, now there's a corresponding operation. Here I am in the input, and instead of one possible next state, if you will, that I could be introducing into my agenda in the parser, well, I could move the dot over these two together, or I could move the dot over one, and then, right? I mean, so you're breaking this up into pieces. You take that operation and the corresponding across a terminal symbol kind of move the dot operation, and you generalize those so that at any given point, you're taking into account the multiple alternatives in the lattice. And it works really nicely. We've used it for segmentation lattices for Chinese. We've used it for sort of morphological analysis alternatives in Czech and Arabic. And I want to leave you with a thought. And this is where I'm going in the next while with this stuff. Intuitively, what's happening here? This sentence is what the Chinese speaker said. Right? There are lots of different ways to interpret it. We don't really want to translate what the person said. We want to translate what they meant. Right? So they could have meant this path through the lattice. They could have meant this other path through the lattice. Right? This is easier if you actually think about, say, the morphological analysis kind of variants of it. But just to give you the idea. Now, intuitively, translate what they meant, not what they said. That leads you to ideas like an interlingua, right? Represent the semantics of what they said. And that way lies madness. You don't want to go there. Because the interlingual approach, traditional interlingual approach, doesn't work. It requires the ability to write down what sentences mean. That's a problem, right? Peace to all the semanticists out there, but we haven't quite cracked that yet, certainly not for broad coverage, right? This is an alternative. Let's just imagine, to keep it simple, that I'm translating from English into Chinese so I can speak the source language, right? And I have a sentence coming in that says, he gave a superb lecture. Just pick a random example. And you want to translate that into some other language, but let's say that superb lecture is not a phrase that was captured in your training data, but excellent lecture was. Imagine starting with what was said, but building a lattice of alternatives of ways of having expressed that meaning. So covering the span of superb lecture, there might also be excellent lecture, right? And covering gave, you might have delivered, right? So you could build a paraphrase lattice, which, by the way, if you know the stuff that Chris Callison-Birch works on, is closely related to ideas of his, and decode the paraphrase lattice. What do you get out of that? You get the idea of decoding by capturing variations on what they said. You're actually the idea of an interlingua goes away and is replaced by this notion of paraphrase. They both capture the same thing. The idea that multiple things, multiple packagings up, there are multiple ways to package a single meaning. But rather than trying to represent the meaning, we just represent the fact that there are lots of different ways of packaging it up. If you do that and use the technology of a lattice to encode that as an efficient representation, we have the technology now to decode that. And so what I'm describing is like the next set of experiments that I'm hoping to do over the next month. So I've taken you all the way to noon or thereabouts, and now I really should stop, and if there are any questions or if Chris wants to come and rescue you and let you out. Questions? People are hungry. When do I get lunch? Okay, there's a question.
I have a question. When you're talking about decoding the lattice, you talked about lots of different ways that you could create the lattice, morphological analysis or paraphrasing or synonym.
You just use your imagination, yeah.
How do you know or decide what's the best way, or you just run a bunch of experiments? I mean, that's expensive to start at the beginning and just try generating lattices in a lot of different ways.
Like anything else, there's art and there's science in this. I would submit that it's a lot less expensive than trying all the different ways, each one in its own experiment, right? So what we've tended to do is take a set of available alternatives that somebody's considered. So for the Chinese stuff, for example, we took the individual character-based segmentation, we took the Stanford CRF segmenter, and we took the Harbin University segmenter. And we did the experiment with each of them individually, too, which is what our team was doing, because it was like, how do we decide on what the segmenter should be? And we put them all together and included them. If you have another Chinese segmenter, bring it on. You know, we'll throw it in and we'll give it a shot. Similarly for Arabic, there's a team at Columbia that is doing some lovely work on diacritization, because without the diacritics, there are different ways you could introduce them, and morphological analysis. Do I keep the owl on there? Do I split it off? Other sorts of things that you could do. Again, it's largely opportunistic. But the philosophy is to get rid of the idea that there's a best way. So given worlds enough in time, or machine cycles enough in time, the idea really would be throw them all in. And then you don't have worlds enough in time, and so you have to make practical decisions. So you limit the branching factor in your lattice. Or you do an initial experiment of some kind and discover, well, these, as individual lattices, these work the best. And this one is really much worse, so we're just not going to bother with that one. We're not going to throw it in on faith that it might help eventually. And those are the sorts of decisions that get made for individual features in your models, too. Right? I want to introduce a feature. That can be expensive. At the team level, right, we're collaborating with IBM and Stanford and CMU and other ones. And the general approach, they're taking Missouri is the show me state. So the IBM approach for does this get into the whole system is show us that this feature or this whatever it is, this new widget or thing that you've got actually shows benefits independent of all this other stuff. And then we'll give it some thought in terms of adding it into the system. It's not quite as draconian as that, but that's the idea, right? You have to do some kind of building bottom up as an experimental strategy, or there's just too much to explore. Other questions? Yes.
I'm still interested in making labels for those different X's, because even if we're not going to commit to those X's being linguistic constituents or anything, there are still independence assumptions that are
going to screw you.
Especially if you use only one symbol for everything.
That's right. That's absolutely right. So let me mention, at the risk of well, not self-promotion, but my own location, my own people promotion. We just did a paper, by the way, the lattice stuff, Chris Dyer was the lead author on a paper we just presented at ACL 08, and what I'm about to say is Yuval Marton, M-A-R-T-O-N, is the lead author on what I'm about to talk about. We actually did some work on introducing soft syntactic constraints as opposed to hard syntactic distinctions and restrictions. So what we did briefly in that work was to say, hey, look, let's suppose we have an externally provided parse tree, right? And let's suppose, for example, that it likes gato negro, right? The Spanish parser decided this is a constituent. There should be a penalty for using this x2 rule here. Label or no label, right? And so you can introduce a soft constraint, either for constituents in general, or you can introduce an individual feature saying, boy, if you violate an NP boundary with one of your rules that the external parser said, you don't want to filter it out. If you filter it out, you lose, because parsers aren't always accurate. And they don't, cover necessarily everything you're always going to see. But if you make it a soft constraint, right, something that gets its own lambda in the model, so that it gets a higher value when it works, right? It turns out that through the magic of minimum error rate training, there are a variety of constraints like this, either for respecting or exactly matching a constituent boundary that your external parser gave you in the source, or violating a constituent boundary that your external parser gave you in the source. We experiment with a whole huge variety. This goes back to your question. If you look at the paper, Yuval actually experimented with just a ton of features, because then you want to try feature combinations too, and you couldn't try all of them at once. And it turns out that you can get some pretty substantial, there's that word substantial, because we were close to 2 blue points at one point there, gains by respecting the source sentence parse tree using soft constraints like this. That's sort of our approach. I was earlier in my career. God, that makes me feel old. I was one of the people who was kind of pushing. This is sort of during the religious warfare between statistical methods and more traditional methods, and I was one of those middle of the road people looking for the balancing act, title of book that I edited. I have since then come to mistrust the knowledge-based resources. My view of them is that they should be no more than soft constraints, that you don't actually want to have them define the space. That was my original conception, that they should define the space over which the statistical model was created. And my view has evolved now to they should bias, as opposed to making hard black and white distinctions between what's in your space and what's not in your space. Yes. Anything else? Okay, thank you guys very much. Enjoy.